1。
那么把3D 人睡觉。
不会的。
Okay. Roshan, you haven't got your test yet. Maybe you can see me in office to see the test you look like during my office hour. Wednesday or Friday. Is it okay? Wednesday 10 to 12 or Friday 1 to 3. No. Cannot. Do you want still to see your test? Maybe I bring it next class, right? Thursday? Yeah. Did you see the solution yet? Yeah, it's on the Moodle. Okay. Yeah. I'll bring it on the next class so that you can check your solution. So this is the midterm scaling for this time. So the passing mark will be scaled to 30, and then distinction mark will scale to 55. So this is the piecewise scaling. Okay, so meaning if you are in this 3 different region here, you will scale by different gradient. Okay or not? Yeah. And yeah. So if you are above 30, then you pass the midterm. If you are above 55, then you are distinction. Okay. And then all the other mark will be scaled using the gradient. 3 gradient here. Any question on this calculation? So for example, if you are marked between 55 and 80, then you will scale using this linear graph. Okay. Yeah. So after scaling, the average is about 71 point something. Okay. Yeah. Understand? Go on. Don't understand. What? 不是很明白。Everyone is affected by this one. So for example, you want to calculate yours or not? Where are you? 30, huh? So the bottom here is raw score, so we start with 30. Okay, and then we see where this 30 get mapped to. Okay, so you are 30. Wait, so I think so you are 30, right? Okay, so wait. Okay, I think I changed my score here. So this one should be a raw score. This is a scale score. Okay, so you are 30, right? So 30. Then you are 55. You are straight away 55. Yeah, you are 30. Okay. Yeah. But if you are in the middle, then you need to scale using the gradient. No, I'm unsure. You want to try your mark? 60. Okay, just try one random number. So 69 maybe. Okay, let's see where 69 get mapped to. So let's try 69, right? Okay. So what's the gradient of M3? So the gradient here is So what do you minus? 100 minus 55 over 100 minus 80, which is 20. So 45 over 20, right? Okay. And then what is that line? M3. What's the line of M3? Y minus 55 equals to 45 over 20 times x minus 80. So you got your y, which is 69. So you want to find your x. Okay, so what is this? 14 e over 45, right? And then plus 80. 86.2, yeah. 86.2. Which is 86.2, is it? Okay. Yeah. So 69 get mapped to 86.2. Okay. Yeah, you can try. You can try and calculate and then you check my record here. Is it correct? Is it matched up? Yeah. Yeah, of course. No, I mean, I mean, this exam is reflecting your ranking. Okay, it's reflecting your ranking. So your ranking won't change. So if you want to get higher score, you need to go up in ranking. Yeah, you need to do better than the others. Huh? I think it's 99. 99. No matter how I scale, that one is fixed at 99, I guess. Yeah. Because you won't go to 100. Because 100 is the fixed point. I think so. Okay or not? Yeah. Yeah. You can try and calculate and then you can check my record, see if it's correct or not. Okay. Yeah. Okay, if no question on this problem here, we will start class. Okay. Right. So let's recall where we left last time. So last time we left at directional derivative. Okay, we left at directional derivative. What do we know? Okay, how to, given a function, okay, how to compute the directional derivative? How to compute the directional derivative? So as a dot product, right? Dot product between two vectors. What's the the two vectors you're looking at? Nebula, nebula F, okay, dot with the direction U. Okay, so you dot two vectors together, you take one of them as the direction you take, and then one is the gradient. What's this gradient function? Still remember or not? This gradient vector here. What is this gradient vector? This vector is built up by the partial derivative. Right? This gradient function is built up by the partial derivative. Okay, that you keep computing before. Okay? The partial derivative with the direction u. So meaning what? Meaning if I want to compute slope in different direction, right? Different direction u, you need your partial derivative at the direction x or direction y. Okay. Okay or not? Okay. So when is this number the largest? When is this? Which direction this number is the largest? Do you remember how we compute this? We need to get the same direction. Okay, we need to get the same direction. Why? Because cos theta is the greatest when cos theta equals to 1. When is cos theta equals to 1? Yeah, when theta equals to 0, the slope is the largest. Next. So this angle you should ask, this theta is what, which direction? What direction? Angle between two vectors, right? Angle, you need two vectors to get the angle, right? Which two vector? Okay, one of them is u. Okay, the other is the gradient. Okay, it's the gradient of the function. Okay, it's the gradient of the function. Okay, so note that theta is the angle between the vector u and the gradient vector. Okay, between these two vectors. Okay, yeah. So remember how we built the plane or not? Remember how we built the plane? What's the equation of plane? The equation of plane. Yeah, equation of plane. Right. So what's the equation of plane? Z minus z naught equals to a times x minus s naught plus b times y minus y naught. Okay. Yeah, so this is the equation of plane. Or we can see the plane as a two variable function, right? Because because z is an independent variable on x and y. If I fix x and y, then I already know what is z. Okay, so I can write like this. Does it make sense? Okay. So what does it mean here? See, these are first variable, right? These are the first degree monomial. Okay, meaning if I differentiate f with respect to x, I just get a. F differentiate with respect to y, I just get b. Okay, so you see the normal vector here. Okay, the norm. Okay, so okay, given let us back out a bit. So given this plane, right? Do you know what's the normal vector to this plane here? Yeah, normal vector to this plane. So last time we talked about you build a plane, right? So what's the ingredient you need to build a plane? How you describe a plane? Give you a plane. How you describe the plane? What is the two ingredient you need? A point and a normal vector. Okay, so what does this normal vector do? So if I give you a plane, okay, you just need two ingredients to describe this plane here. You just need a point on this plane and a normal vector. Okay, why is it so? If you get the normal vector here, all this plane, all the points on this plane, okay, will form a vector which is orthogonal to this normal vector here. Okay, all of them. Okay, all of them on the plane. Okay, if you take all the vector you build, okay, from all the point in this plane, they are all orthogonal to this normal vector. Okay, and then how to read this normal vector from this equation of plane? Hmm? How to read? How to read? It is just a, b, and minus 1. Okay, so you read off the coefficient in front of these factor. Okay, or not? Okay. Okay, so in front of z minus z1 is 1. Okay, but how to read it properly? So really, you need to turn this equation into a times x minus x naught plus b times y minus y is naught, and then minus z minus z naught equals to 0. Okay, and then all the coefficient in front of this factor will become the normal vector. Yeah. Okay. Okay. And then what's special about this plane here? So this plane here, you can compute the gradient. Okay, gradient of this plane. Okay, what's the gradient of this plane in this case? What's the gradient of this plane? Let's see. What's the gradient of this plane? What is gradient? Definition of gradient. Yeah. What is the definition of gradient? Yeah. Hmm. How about I remove the evaluation here? As a function, what's this? Delta f, nebula f. Huh? So what is nebula f? What is gradient vector? So in one variable, right, gradient is what? Is the slope. Right, is the slope in one variable gradient. But two variable, how? I got so many directions to take. Okay, so you need to take the important direction. Okay, if two variable, you need to take two important direction, which is x and y. Okay, because they are linearly independent. If three variable, you need to take x, y, z. Okay, and then for higher dimensional, you need to take derivative at different uh, direction on the basis element. Okay, so for example, in this two-dimensional case, okay, what is important? Which partial derivative is important in two variable case? Fx and Fy. Okay, so Fx and Fy form the gradient vector. Okay, gradient vector for your surface. So for plane, okay, so for plane, what is the gradient vector here? AB, good. Okay, so this is the AB. Okay, so AB give you the gradient of the function. So if you find, okay, if you find the directional derivative at any point, okay, so which direction is the steepest? Which direction is the steepest? Which is the steepest? So 最斜最陡 okay, it is when is it the steepest? It is when the directional derivative get maximized. So when does directional derivative get maximized? So you need to think again about the dot product. So when's the dot product maximized? Yeah, theta equals 0. So when is it? When is theta equals 0? When you take the same direction as your gradient vector. Okay, I show you one video. Not the god anymore. Yeah, the one. Let me see. Cannot play. Where cannot play? How come? I think cannot play. Maybe later I show you again after the break. Okay, later I'll show you. So uh so the gradient of a plane is just the first two part of your normal vector. Okay. Later I'll show you one video. Okay. So today, as discussed last time, we will prove a theorem. Okay, we will prove a theorem. So we'll prove the theorem that how we obtain the directional derivative. Okay. Let me get the statement first. Again, so let's repeat the statement. So theorem, if f(x,y) is differentiable, then the directional derivative of f is obtained by the dot product of the two vectors. One of them is the gradient vector. The other one is the direction vector. Direction vector. And where u equals to AB, and then the length of u is equals to 1. Okay, so you need to take the unit vector. Okay, or in other words, you can open this up, expand it. It is just fxxy times a plus fy xy times b. Okay, so we're going to prove this today. I just only want to plead you one thing. There's one thing I want you to do. Don't sleep. Okay, don't sleep. Keep yourself awake when I go through this proof. Okay, and then actually this proof is quite related to some of your project. So if you can understand this proof, probably will help with your project proof. Some of you. One of them is Jinsen. Okay, so be careful. This proof is related to what you are reading at the moment. Okay. Okay, please don't sleep. Don't understand also don't sleep. Okay. Please don't sleep. Okay. All right. So we'll prove this. Okay. So what is this? Last time we said already, this directional derivative is a what? It's a point or a function? Function. Okay, it's a function. You put x, y into it, you get you a number. Okay, you get you a number. So it's a function. So you want to prove that left function and the right function is the same. Okay, so what you should do? When you check two functions to be equal, you need to check at every point. Okay, you check at every point. You need to show that at every point they equal. Okay, at every point they equal. So let's do backward. Let's do backward proof. So mathematics is like this. We work backward and then we show people forward. Okay, so meaning we want to check this is true at every at x naught, y naught. Okay? For every for s naught, y naught. Okay, it's true. Okay, so how to prove this? Okay, how to prove this? Okay, so how are we gonna prove this? Right. So what to do here? Okay, so what can we do? So the first thing you think is how you gonna build this right hand side thing. Right? How to build this right hand side thing. So one thing you can do is how about look at one function. Okay, let's look at one function here. So define one function. Okay, what's this function here? This function depend on h. So what does this h do? Okay, I try and perturb my f a little bit away from my s naught, y naught. Okay, instead I look at this function here. Okay, I perturb a little bit away from s naught, y naught in the direction of AB. Okay, in the direction of u. I perturb a little bit. Okay. Okay. Maybe at first you don't know what is going on here. Okay. What are we trying to do with this? Okay. So remember what? Remember what? What can you do? What can you do with it? How far is this f away from f prime? Okay, so you need to recall the definition of limit. Okay, you need to recall the definition of limit, right? Okay. So for example, what can we do? Let's differentiate it. Okay. Let's differentiate g prime f. Okay, so what's differentiating g prime f means? Huh? 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 remember last time we learned this kind of thing before? The differentiation implicit or chain rule. Do you remember or not? Like something like this. So we got the f and then x naught ha something like this. And then we differentiate f with respect to the bottom variable or something like this. Do you remember or not? Okay. Yeah. Okay. So if you want to differentiate g, maybe you can try this way. Okay. Or we can go into definition. Okay. Let's go into definition. Then let's differentiate at a particular point 0. Okay, we'll go into definition. So what is this definition here? So this is GH minus G0 over H. This is one variable differentiation. Okay. Okay, we'll follow this step here. One variable derivative. Okay. But we know GH here. Okay, and we also know G0 here. So we can just sub it in. Okay, so we reach to this step here. So what is this? What is this here? So what is this limit here? What is this? So you make changes in two directions, x and y. Okay. Is that? This is just the definition of directional derivative. Okay. So what I'm doing is I just expand this definition out. Okay. For this step here, I just expand this definition out. Okay. Yeah. So this is the definition by definition. Definition of directional derivative. Okay. So how is it useful for this guy here? Okay, how is it useful for this guy? So we're gonna do something like this. Okay, we're gonna do this. What do we call this? Chain rule. Okay, we're gonna do this chain rule. Okay, so we can go the other direction. Okay, what direction we can do now? So if we do G prime on H, okay, what do we get? So what we get is df over dx over dh plus dh over dy times dy over dh. Okay, so you can note that there's no x and y, right? Okay, so what I do is I just rename these variable. I just rename the variable. Okay. Yeah, I rename the variable. Okay. So after renaming, so what do I get? So I just get fx xy equals to a plus fy xy plus b. Okay. 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 And then what happened? So here is g prime 0, right? Here is g prime h. Okay. So what do I do? So okay, I expand it up. Okay, let's expand it up. So fx of s naught plus ha, okay, comma y naught plus hb times a plus fy s naught ha y naught plus hbb. Okay. Let me move this now. Okay. Okay. So what's the difference? So let's see. This is g prime h, right? So this is g prime h. Okay, so this is g prime h. And then What's our goal? Our goal is here. What is the difference between our goal and this number here? This expression here. I got S0, Y0. I also got S0, Y0 on Fx, Fy, okay, times A times B. But we got extra HA and HB here. Right or not? So what to do? How to remove this HA and HB? How to remove HA and HB? Just let H equals to 0. Okay, we just let H equals to 0. And then we can compute that G prime 0 is equals to Fx of X0, Y0 times Z plus Fy of S0, Y0 times B. Okay, but we have two ways of getting this G prime naught. So first way is this du. Okay, second way is this. But they both equals to G prime 0. So the left hand side is equal to the right hand side. You know. Okay. Any question? Any question? So first way is you use the definition. Again, second way is use the chain rule that we have learned before. Okay. Use the chain rule we have learned before. Okay. Because all these this is in terms of h, and then this is also in terms of h. Okay. Okay. Now, any question? If you start, just ask which part you start, and then we can try and go through it together. Okay or not? So this is the part of 3 we learned last time. Okay, and then the definition need to be used. So improving, right? Improving definition is very important. We only can prove from definition. There's no specific example we can work on. Okay. So that's why definition become very, very, very super important in pure maths. Yeah. Any question on this proof? Yeah. No? Yeah.
What does the right
Most. Rightmost term on G prime H. Rightmost. You mean this here? This one. This one I just rewrite this notation here. I rewrite this notation. Okay. So first is this f prime x. So what is dx over dh? Based on the change of variable, what happened? So let me put here. Dx over dh is what? D of x0 plus ha over dh. So what do you get? S0 is fixed. A is fixed. So you get A, correct. Yeah, so you get A. Yeah, you get A, correct. So for this term, dx over dh, you get A. Dy over dh, you also get B. Similarly. And then del f del y, I just rewrite the notation. Yeah. Any question? Other question? Okay, if not, we go through second proof of this thing. Okay. So I think maybe this proof is a bit tricky. Okay, because we try to construct something extra. Let's try a direct proof. Okay, so we have a second proof here. So what do we want to show? Okay, let's remind us what we want to show again. So du fxy, okay, is equals to fx xy times A plus Fy xy times B. Okay. So let U equals to AB again. Okay. So how to show this thing? So the easiest thing is you just expand the left hand side and then see that you get the right hand side. Okay, this is the usual thing you do. So meaning you start with definition. Okay, let's start with definition also. So what's the definition of du again? So you make small change in the two direction. Okay, in two direction. So the difference between this proof and the previous proof is this we straight away deal with function. We don't deal with point. We don't check at every point. We straight away check function. Okay, we straight away do computation function. Okay, but so what's our goal here? So our goal here need to somehow stop at here fx xy times a plus fy xy times b. So we need to somehow stop here. So how is it happening from this limit here? Okay, how are we going to evaluate this limit here? Okay, so there's one condition that you haven't used in the statement. What's the one condition the statement give? F is not just continuous. It is differentiable. It's stronger. It's differentiable. Not just continuous. It's continuous, maybe not differentiable. But F itself is differentiable. So last time I told you that we don't need use the definition to compute derivative, right? But we need it for this proof here. So what's the definition of F is differentiable? So let us record it. So what is F is differentiable? Let's record this here. Okay, so for differentiable two variable function, you have this. So if you make some changes in x and y, and then it's equal to the FAB plus FXAB delta x plus FYAB delta y plus some epsilon term. Okay, this epsilon term will disappear when I make the changes for. So you see, in differentiability, the two partial derivative pop up. Okay, the two partial derivative pops up. Okay, so let's try this. Let's try this. This is equal, right? So let's try this. So let's cut this. Let's cut this. Huh? So let's cut this. So since f is differentiable, right? Okay, so we can replace the first term here. Okay, we can replace the first term here using the definition. Okay, let's replace it. So we have fx plus ha, so become fxy plus fx of ab, which is xy in this case. Delta x here becomes ha plus fy of xy. What is the delta y here? Y plus hb minus y. You get hb minus, oh, we still have the epsilon term. So epsilon 1 hb plus epsilon 2 h, okay, epsilon 1 ha and then epsilon 2 hb minus fxy. And then everything over h. Everything over h. Does everyone agree with this line here? Agree with this substitution here? Since f is differentiable. Okay, by definition, I replace my fx plus ha and y plus b. Does it make sense? Does it make sense or not? Making sense? So I replace the left-hand side with the right-hand side here. Okay, everyone follow? Okay, follow? Okay, so What do we do next? So we just simplify the terms here. Okay, so we cancel fxy and fxy. You see there's a cancellation you can do. And then what happened to the rest? All of them has h. I am dividing by h. So you can see or not, this derivative dividing by h is not a coincidence. Okay, that's what we want it to be. Okay, so after cancellation, what do I have? fxy times a plus fy xy times v plus epsilon 1a plus epsilon 2b. Okay, we're left with this. So are we there already or not? Not yet there. So what happened? What's the extra thing? Epsilon. So how to get rid of the epsilon? Can we get rid of the epsilon or not? Can we get rid of the epsilon? Yeah, what does the differentiability tells you? When the changes go to 0, epsilon also go to 0. So the changes here refers to what? What's the changes here? Delta x is what? HA, delta y is HB. But we're taking limit of h go to 0. So meaning epsilon 1 and epsilon 2 will go to 0. Okay. Since they go to 0, the constant times them also going to 0. Okay, this is what you learned last time. So in the end, you get the answer you like here. Okay. This is what tested in last year final. This question. Yeah. How about this year? We'll see. Yeah. We'll see. Okay. So at least this I think for me, this second proof is more intuitive. Because I just apply definition and then apply definition and then work out. Okay. Previously is what analysis people will always do. Okay, they will try and make their proof a bit fancier. Yeah, they try to define something new things, but actually, yeah, the way they look at problem is a bit different, I guess. At least when I see it. Okay or not? Okay, so this is the proof of directional derivative. That's why the directional derivative is a dot product of two vectors. Okay. Since we already do until this stage, right? Let's introduce the proof of implicit function theorem, but we won't do it now. Let us recall what is implicit function again, and then we will do it after the break. Okay, so what is implicit function theorem? Let's recall this implicit function theorem here. So, okay, so what is an implicit function theorem? So you start with a function fxy equals 0, okay, and then there's a point, okay, x naught y naught, such that it is on the surface, okay, on the surface, fs naught y naught equals 0. Let's suppose that the two-dimensional derivative is continuous, are continuous, and then moreover, the partial derivative at y, okay, at that point is not 0. So this is a crucial point where you can replace your y in terms of x. Okay, so you can rewrite. So for this part here, let me draw something. So for this part here, you can rewrite fx y equals to fx dx. Okay, y also in terms of x. Okay, and then you want to show that dy dx equals to partial f over partial x divided by partial f over partial y. Last time I give you a slick proof because that proof might not work at some point. For example, the point where this is 0. Okay, so we can always move it around to avoid this case. So later we'll see how to prove this. Okay, using similar method, using the chain rule, using the definition of derivative. But you can think about it, how to prove it. Yeah, during the break if you like. If not, I will show you after the break. Okay, so let's break until 4:01. Then we will resume.
这你要用 calculus 2的东西，给他，他们知道啊，知道啊。但是我看到第一条里就这个，哪个理论？不然你来做这个，好，不然做这个高维，这个是一维的，就是放个船的。然后你做这个做这个高维的吗？嗯，他们就是别人那有些是。哦，啊，啊是，这里这个关于。接触不了多的事，啊，这个简单好多。没关系，这个才几克吧？这么一奥克的奥数，这个怎么说？哦，它这个是直接也够了，不然就是不行了，什么东西？同样难。嗯， 这个这个这个这个是真的。And then 你想把这个东西写在上面，我不能去。但是理解不是他们对，为什么这个？对吧？对啊。上面就有人拉你这边。
Julian, have you decided you still pick are you still choosing the topic?
我想用我说的。
But like the content I guess is not enough. Have you tried and write it out already? You write the draft already? Yeah. Deadline? Yeah. Maybe you try and write it out because I require 1.5 page. See if it's long enough.
我感觉说有点。
You can try because I cannot imagine because for me it's like few lines. Yeah, you try and show me what you have, and then see we can add some extra stuff or not if required. Okay. So next Tuesday is the due date, so make sure you send me this week the draft. Yeah. Also for the rest, please if you need to check the draft, please send me by this week, and then next Tuesday is the deadline. Okay, and then I will set out the one link for you, which is the turn it in. So after I check the draft, you happy with the correction, go and check whether you have plagiarism or not. Okay, and then submit your project with turn it in report, your own report, and then the cover page, which I will post up with the assignment link in Moodle. Okay, so 3 things you compile together. Okay, cover page, your project, and then turn it in report. Okay, so turning report, you don't be worried if your percentage is too high due to definition. Is it okay? Okay, I don't want to be like the whole part of introduction get penalized. That one cannot. Okay, that one definitely cannot. So I will just check the highlighted part. Okay, even it's just definition, I just let it go. It's just definition, it's universal, so I cannot do anything. But the thing that you wrote, the paragraph, those will be penalized if you get a highlighted. Yes. Yes, together. So cover page, your report and turn it in report. Your project and your turn it in report. 3 things put together, submit on Tuesday. Before yeah, submit as one file. You compile as a PDF. Okay. Yeah, I will put the instruction again when I set up the thing. Okay. Seng, fix already your topic. You happy with that one? Okay. If you want to do that one. Already found proof. Okay. Actually, that question people did it before. Actually,
Screen contract.
thing called text picture or latex draw. If you use latex draw, you draw it and then it will generate the code for you, latex code. Or you can use text picture to draw it, text CD or text picture. Actually, your project is done by one student before. You can try and have a look. Yeah. It's called Seng you can check. You can check. It's in the file I put on. Tony, you want to ask some? You want to ask anything? Hey, how you get your format? Huh? Yeah. You make it yourself or where do you find the format? So similar to my paper, the journal. I post out my paper for you guys, right? That format. So he's like almost the same as the format. Yeah, I post out this where's it? Let me see. Okay, I post out this paper here, right? This is my paper here. So the purpose of the project one is for you to practice to write a maths journal, maths article. Okay, but it's just a simple one. Just some result that people do before you recollect it, you write it on Word. That's all. Okay. So this is what just publish. Yeah, this is the stuff I do in my thesis. I guess after abstract algebra, you will know what I'm doing. Only you will know what I'm doing. But what I want to say is, even you don't know this term, right? You don't know this term, right? You should be able to follow the logic of this line. Okay. So max article is like this. You cannot learn all stuff, okay? You cannot learn all stuff. So how do you study? Okay, how do you study max? How do you study max? You need to get the logic right. Okay, so for example, let me tell you how to read this sentence here. Okay, so how you read this sentence? Okay, maybe Sing tell me how you read this sentence. How about abstract? How you read abstract? Tell me what do you think? How you feel when you're reading the abstract? Or you read it and then you tell me what the abstract do. Yeah. How to read a maths article? Abstract. After you read, tell us what you read. No. No need to tell me what it means. What happened? What happened? What happened? What happened? There are only two sentences here only. There are only two sentences. Okay. Okay, what happened? So first sentence, what the first sentence tells you? What does the first sentence tell you? And 一个东西 is what? Uh-huh. 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 Okay, let me replace with this line here. Okay, so what do I do? So how do you read this sentence? So we show that, okay, show that something, something. Okay, something also known as, what is known as? What is known here? What is this known as referring to? This known as referring to something just before the known as. Okay, so this finite dimensional equivalent algebra is what called this type B algebra. Okay, and then we show that something, this big thing here, is some other thing. Okay, some other thing. Like this. Some other thing. Okay. So we show that what? We show that a certain category of bimodule is a quotient category. Okay. Yes. Can or not? So you need to be able to abstract what's the object, what's the adjective. Okay, you need to abstract what's the object. So the main thing here we can reduce as we show that a certain category is a quotient category. And then you need to ask, what's the category you are showing? What's the quotient category you are showing? So the category you are showing is the category of bimodules. Okay. And then what's the quotient category? Quotient category of the category of another category. Okay. But you don't know what happened. You still don't know what is bimodule. You still don't know what is finite dimensional algebra. You still don't know what is a typing Zegel bimodule. But you know how things get connected. This is what I want to convey to you. You get what I mean? This is what max degree can give you. So why people say max degree is versatile, is versatile, is versatile? I can give you a computer science book, and then you read it. And then you can know how these computer system get connected together. But if I go ask you to build a computer, you don't know how to build. But at least you know how they connected. And then you can try and do hands-on. You understand? You understand? Okay, so what mathematics degree can give you is the logic. Okay 了，所以一本天书丢给你，你都要会读得出来。Okay 了， you know? So very difficult book throw to you. You also need to figure out what's the logic behind and then read it. For example, the Richard Feynman. Do you know Richard Feynman? Richard Feynman. And every time I show some phrases by Richard Feynman, there's a guy. Richard Feynman is a physicist. He's a Nobel Prize laureate. He you know what he did? Okay, he did experiment and theoretical physics, but he is able to translate an ancient language which nobody know before. So I give you an ancient language, okay, like something drawn on the wall. How you decode the language from nothing. So when people wrote down the language, right? Why people say, for example, what? Like pisang goreng. Does anyone know pisang goreng? Fried banana. Okay, so you see, very interesting one. This is the first thing I confuse when I learn English and BM. Okay, so fried banana. Okay, so this one is how to write jiao. Like this one. Okay, so fried banana is 炸香蕉。你会讲香蕉炸吗？ No, right? Or banana fried. But in Malay language, they call it pisang goreng. Okay, pisang is banana, goreng is fried. So you see, in different culture, different language, they call for different option, you know. Only two words, either one at first, one at the back. But two different culture, they use different expression. Actually, Japanese language is similar to BM. They also put the important stuff first. Okay. So I give you a random language, how you decode the logic. Okay, when people speak a language, they have a logic behind. Okay, so how you decode the logic. Okay, why the Malay people think like this? Maybe they think that the pisang is more important than the goreng. Okay. Maybe we think that fried is more important than banana. Maybe it's fried, maybe it's steamed, or steamed banana. Or what else you can do? Boiled banana. Maybe sound a bit disgusting, but yeah, right. So yeah, depend on what culture emphasize more. Okay, yeah. Okay, now. So the logic is what I want you to get from this when you study the mathematics. Not just solution, okay, not just computation. Okay, we don't care much about that. Okay, at least for pure maths. We want to see how you solve the question. Okay, how you solve the question. All right. Okay. Let me see where we stop. Okay, let's do the proof for implicit function theorem here. Okay, so how we achieve this? How do you achieve this? So, proof. So let's prove this. So what is our goal? Okay, always remind what is our goal first. Okay, 你要有目标，对不对？对吗？思颖，比赛一定要有目标，对不对？不然去比什么赛？对不对？啊，we prove we also have goal。啊，不需要那个字，不需要，那个字不需要，那个字不需要，那个字不需要。The remark is not important, but what is important is this theorem here. Okay, so what's the goal? Okay, we need to always keep our goal in mind. Okay, so our goal is to show that dy dx equals to minus del f del x over del f del y. Okay, this is our goal. So how to achieve this goal? So to achieve this goal, you don't say, I don't know what is f, I don't know what is x, I don't know what is y. You want to achieve this goal. Impossible, right? You want to win the ping pong competition, you must know the ping pong, right? Right, correct. You need to know the technique, right? Correct. Okay, so what to do? Okay, so what to do here? So what do we have? Okay, what do we have? So just now we say that we have a special condition. We can write x in term y in terms of x for a small region. Okay, for a small region we can do that. Okay, so we can write fx fxy equal fx vx. Okay, for a certain small region. Okay, such that it is differentiable at AB. Okay, at AB. So why we can do this? This is explained in the remark, if you like. Okay, so by remark before. If you don't get the remark, you just accept the fact that we can do this. Okay, just accept the fact we can do this. So if you accept that fxy can be written in fx and vx, so what can we do here? It's differentiable. Okay, it's differentiable. So what do we do if it is differentiable? We can use the definition of differentiable again. Okay, we can use the definition of differentiable again. So this is differentiable at where? F at A, B. Okay, at A, B. So in this case here, this term here is equal to FAB plus Fx of A, BA times the difference between x and A plus Fy at A, VA. Of course, I can put B here, but let's put VA of Vx minus Va. Okay, plus delta 1 times delta x. So here is x minus A plus epsilon 2 times Vx minus V. Okay, so this is by definition. So let's put here by definition. Okay, by definition to get this. Different definition of differentiability. Okay. Remember the square just now we put out that one. Okay, you need to apply that. Okay. So what's the advantage of applying this? That what? AB is a point on my surface. So meaning it satisfies FAB equals to 0. Okay. XY is also a point on my surface. So it also satisfies FXY equals to 0. Okay, so the first two terms here disappear. Okay, what I left is the thing behind. Okay. So here y Vn Ex minus Vn plus epsilon 1 x minus a plus epsilon 2 Vx minus Va. Why is it true? Why is it true? Since xy and AB are on points satisfying fxy equals to 0. Okay. Okay. Okay, I see. Iban. Okay. At least following is okay. Okay. Any question or not? Before we continue? Yeah. Or anyone want to ask why xy and AB satisfy this? Why? You don't know. Oh, you don't know. Okay. So why? Okay. So why? So what are we doing here? So let's read here again. Okay. So this condition here, right? Fx and Fy are continuous at a point. Remember last time when we talked about when is a function differentiable? Either you use the definition limit, go and compute it, or you have a theorem. So the theorem is if the first partial derivatives are all continuous, then f is differentiable. Okay. So since we know that fx and fy are both continuous at some point, actually this s naught y naught here is what we call ab just now. Okay. So it is differentiable there. Okay, it's differentiable. And then this xy, right? The xy we look at is all the xy near this point, P naught, which is AB. Okay, so we just look at near around P naught. Okay. And then all these points will satisfy fxy to 0 by setting. This is the setting. Okay. Okay. This is by setting. See, this P naught here satisfy fs naught y naught to 0, meaning it is a point on the surface. Does it make sense? Remember the plane, right? So what is the point that evaluate to 0? Where's the plane? Let's get the plane back. So you should imagine this in your mind. This thing here. Here. It is something like this. Some function in terms of x, some function in terms of y equal to 0. But this one have extra condition. That's why this point will live in R3. Just now the point is living in R2. Okay. Okay. So it is some equation like this give you a surface or line. Okay. Okay. Any question? Maybe Chun Jack got question. Just ask where you start. It's okay. I can guide your question. So far, okay. Okay. Let's go back here. So all these xy are the point on my line or my surface. Okay. All right. So until this point here. Okay. Until this point here. Okay. So we are almost done already, actually. We are almost done already. Remember my goal. What's my goal? dy over dx equals to minus of the x partial derivative over y partial derivative. Okay. I already have x partial derivative here, y partial derivative here. Okay. So where do I get my dy dx now? Okay, where do I get my dy dx now? So where did you see y x inside this equation here? My y is actually already rewrite in terms of x. Right? Remember what did I write just now? We can write y in terms of phi x. Okay, around at that point here. So what can we do? So let's play around with these equation here. Okay. In particular, what can we do? We can move. Let's see how we move this. So we can write it as phi x, okay, equals to phi a. So I move this part here. Okay, I move this part. I split out the phi x from this factor here. Okay, so let's split this. So I get minus fx a phi a times x minus a over fy a phi a. Does everyone follow what I'm doing? So I move fx to the other side, become minus, and then I divide by fy. Okay, okay. So because I want to keep this Vx staying here, right? So probably I need to move all the delta epsilon term away as well. Okay, let's move it away. Move it to the other side. So I think I should get minus epsilon 1 x minus a plus epsilon 2 dx minus 3a. Okay, so what does this say? This says that for epsilon 1, epsilon 2 will go to 0 as s going to 0. This is the differentiability give you. This is what the differentiability will give you. If I make the changes smaller, the epsilon and epsilon 2 will disappear. But what is this? What is this? What is this? What is this? This is actually the differentiability of Vx. This is actually the differentiability of Vx. One variable differentiability. Okay, so these will imply that dy dx equals to minus Vx over Vy. Okay, so if you cannot see this, let me write one more sentence for you. So we can rewrite this sentence. Vx minus Va. Okay, we can divide by x minus a equals to what? Minus Vx a Va over Vy a Va and minus so here minus epsilon 1 plus epsilon 2 of Vx minus Va divide by, okay, let me move a bit. Okay, so here we get phi epsilon 2 times Vx minus Va over x minus a. So what do? I just move Va across, okay, and then I divide by x minus a. I divide by s minus a, okay? I remove the factor here, I remove the factor here, and then I divide here by x minus a, correct? Okay, and but what? When x go to 0, so when x get approach, okay, so should be a, sorry. So when x approach a, right, x epsilon 1, epsilon 2 disappear. Okay, but what is this part here? Vx over Va over some distance going to 0. This is the derivative. Okay, so this is the dy dx. Make sense or not? Does it make sense? So what's the principle here? So the principle here is you write down the differentiability of f, the definition, and then use the property of fxy equals to 0 to throw away a few terms, and then rearrange until you get dy dx. Okay. So this is what you need to do. Okay, no? Yeah, I will post out the proof and then you can read again. Okay, you can read again. Because maybe you are first time seeing so many symbol definitions, so you confused. So what's the main tool you need here? So the main tool you need here is differentiability. What's the definition of differentiability? Okay, this is the main thing you need. Differentiability, and then what's the condition? Okay, that question give you. What's the function? What does function satisfy? Okay, in the statement. Okay, and then you move around, move around, move until you get your target. The most important thing is your target. Make sense? Okay, I will post out the proof and then you have a look. Yeah, see if you understand it. If not, we can discuss next lecture. Okay. So today we discussed two kind of quite heavy proof for you. So please have a look, study. Okay. Yeah. So mainly it's on the definition of differentiability. So you need to really understand or not understand, just pick out the definition of differentiability. Okay. Yeah. Definition of differentiability. Very important. Okay. Any question before we leave the proof? Proof or the proofs? Any question before we leave the proof? Okay. So it's normal that you don't get all the detail right, but you can study again later. Okay, when you do revision. But you need to get the logic right first. Okay, use the logic and then do the revision. Yeah, no? Okay. Yeah. Yeah.
What exactly?
What exactly is fx and fy? You mean partial derivative? What exactly? Oh, what exactly? So remember last time we talked about this fx and fy. So meaning you have a surface. Okay. So fx means you cut along the what's the plane? What's the plane that cut through x-axis and z-axis? Is the zx plane, right? Zx plane. So you use zx plane to cut through your surface, and then you see the gradient. So when you cut through these two surfaces, right? One is plane, one is another surface that's orthogonal, probably. Then you will get a line. Okay. Once you get a line on the zx plane, you can compute gradient and h bar. Okay. So fy similarly, you cut through your surface using the zy plane, and then you get the curve. Then you can compute the gradient. So this is fy. Yeah. Okay. Yeah. Okay. Right. In that case, let's do some computation to here. let's do some computation on this. Maybe you try 3 minutes, see if you can work out anything from here. Yeah. So just now I teach some very abstract stuff. Now suddenly come back to some very practical stuff. This is typically what the mathematician doing. So we discuss very abstract ideas, and then somehow we need to straight away come back and do example. Okay. So this is what the daily routine people did when I do maths. Okay, so suppose that a bar is located on the hyperbolic paraboloid. Okay, z equals to y squared minus x squared at the point 110. In what direction should it move for the steepest climb, and what is the slope as it starts out? So steepest climb. So this is looking for a maximum directional derivative. Okay, maximum directional derivative. So there's a point 110. So which direction has to go? It has to go to get the maximum steep. Which direction? 110 is the point, right? So which direction you will get the steepest climb, which is the maximized directional derivative? Collinear? Not really. Oh wow, collinear meaning they same line, right? Yeah, same direction with what vector? When does directional derivative get maximized? Orthogonal? Yeah. Perpendicular to what? Okay, let's recall again. Keep recalling. So when does this number get maximized? Yeah, when does this expression get maximized? When theta equals 0, meaning u has the same direction with delta f, nebula f. Okay, so meaning you need to find the gradient of f. Where you need to find the gradient of f. Okay, so let's find it. So what is the delta f here? So delta f here is fx, fy. Okay. So what is f differentiate with respect to s? Minus 2x. Okay. And then differentiate f with respect to y. Minus just 2y. Okay. So is everyone okay with we just set f equals fxy equals to y squared minus x squared? Is it okay? Everyone can follow the step here. Because z is a dependent variable of f and y and x. So we just set this is the surface is just fxy equals to y squared. Okay. 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 So which direction you need to pick? So at P110, the point 110, delta of F11 is just minus 2, 2. Okay, minus 2, 2. Okay. And then what's the slope? Okay, so here they ask for the slope. Slope is what? is the gradient of the line. Okay, so how to get the slope? How to get the slope? How to get the slope? Right? So one by one by one. So then how do you understand? So this me read fx 1 -2 and then plus fy 1 times 2. Okay, so let me write down this. So because you are using the definition, right? duf 1. This is duf. So this is the slope. Okay. So in this case, what is this? This is -2 times -2 plus 2 times 2, which is there something wrong here or not? What is this? 8. Okay. This is 8. So what do you do? What do you do? Tingzhen, what do you want to say just now? Same. Okay. So is this correct or not? Did I do anything wrong here or not? Is this correct or not? Let's think about it. Is this correct or not? What's the condition in my U? What's the condition in my U? Same direction. Any extra condition or not? There's a Seng trivial condition, right? U has to be what? Huh? Someone said what? I haven't say. I haven't say what? No, say. What did you say? The length of the U has to be 1. We are using the unique vector here. Right. Remember last time? Okay, because we don't want to have the effect of U affecting my directional derivative. Okay, I need to pick a U which is unique length 1. But it's -2. What's the length of -2? What's the length of this? What's the length of this? Square root 8. Okay, so this is not length 1. Okay, so this is not length 1 vector. We cannot just substitute in. So how to make it a length 1? Divide by square root 8. Divide by 8 or square root 8. Square root 8. Okay, let's try. If I divide by square root 8, divide by square root 8, right? Okay, so what happened? So I'll check. Okay, check that this is a length 1 path. So let me. That's 2 over square root 8. And 2 over square root 8 is length 1. Okay, that's it. Okay, so you need to make sure the direction you use is length 1 first before you apply. Okay, so in this case here, what's my answer? Become. So I need to divide by square root 8, divide by square root 8. So divide by square root 8. So it is 8 over square root 8. Square root 8. Yes, square root 8. Okay, which is 2 times root 2. Okay, yeah. Okay, so make sure that when you compute these directional derivative, make sure that your direction is unit length 1. Okay, make sure your direction is unit length 1. Okay. Any question? Okay, so how do you see this in your picture here? Okay, so let's say this is your hyperbolic paraboloid. Okay, so let's find where is 1, 1, 0. So 1, 1, 0. So up here. Okay, 0 is here. So probably up here. And then the direction is where? Negative 2, 2. Okay, negative 2, 2. So you need to find where is negative 2, 2. So negative 2. I think it's in this direction, and then 2 is in this direction, so around this direction, I guess. Negative 2, 2. Okay, and then the slope is positive, so that's why this surface going up. Yeah, make sense? Does it make sense? Okay, yeah. Okay, so what we are computing, really, you need to take a plane and go and cut your surface. Okay, get your surface, get a plane, cut it in the right direction. And then you will see what's the directional derivative you get. Okay. Okay. So here is 443. 443. Maybe we'll go into a bit next subtopic and then we'll continue after the break. Let you sink in first and then we go continue after the break. Okay. So next subtopic we talk about tangent plane to level surface. Okay. So you just imagine I have a surface here. Okay. I want to take a tangent plane at the top. Okay. So suppose that S is a level surface. So why we choose level surface? Because we want to look at some equation equals to K. Okay. Right. So just now implicit function theorems when the K is equal to 0. And then we reduce by one variable. But now it's more general. We add in extra dimension. We look at surface instead of line. And then it's equal to some constant. Okay? Some constant. Not just 0, but some constant. And then let again x naught, y naught, z naught be a point on x. Okay? Because we want to study the tangent plane over the surface. So definitely we need to pick point from the surface. Okay, for example here, I want to pick point here, I want to pick point here. Pick the point on my surface. Okay, so picking point from the surface means what? It needs to satisfy the surface equation. They need to satisfy the surface equation. And then what can I do? I can imagine I'm an NC. Okay, you are an ant. Okay, you are C, right? So you work on the surface here, but I'm only interested in the path that pass through the point of interest. Okay, in this case, here is S naught, Y naught, Z naught. So let C as a path that lie on the surface and passes through P. Okay, so let's say P is here. I can look at all paths that passes through P. Okay, any path, but passes through P. And then what? And then we want to find the tangent plane. So how to find this tangent plane here? So somehow we can work it out through this path. Okay, we can work it out through this path here. So what do I do? So what happened? So note that this path, right? This path here, ST, YT, ZT here. Is it true that all the point in the path lies on the surface? Is that true? Is it true? When you walk on the surface, right? Is it true that every point, every step you step is on the surface? Is it true? Is it true? I'm not trying to trick you. So if you are walk on the surface, right? Okay. Also, this is the surface. Okay, you walk on the surface. You have a path, right? Is it true that every step, every point here is on the surface? Huh? If it's not flat, it's also true, right? if it's curved, because I'm moving on that surface. So every step I step is stepping on the surface. Correct or not? So meaning what? So meaning every point in the path satisfy the surface equation. Okay. So every point in the path satisfy the surface equation. So I can write like this. Okay, I can sub my path into the surface. This means what? So I make this surface evaluated on the path. Okay, so I have a one variable path here. Okay, and then what is this? This is kind of familiar stuff, right? I have f in terms of x, y, t and s, y, z, but my s, y, z is coming from a path. Okay, so what can I do? I can do chain rule again. Okay, I can do chain rule. Okay, I can do chain rule to on this actually do implicit function on this and then do chain rule. And then I get this here. Okay, I get this here. So how many paths from big F to T? So there are three paths. Okay, there are three paths, and then you need to take the sum of the concatenation of these paths. So you need to take the product of them. Okay, that's why you get del F over del X times del dx over dt, and then del F over del Y times dy over dt, and then del F over del Z times dz over dt equals to 0 because you're differentiating a constant with respect to t. So what is this here? What is this? This is again a dot product. Okay, again a dot product here. So we can write it as del big F dot r prime t. So what is r prime t here? So let's recall what is RT. So RT is a parameterized path. Okay, it's a parameterized path. So these coordinates are given by the time t. Okay, and then how to differentiate this path is just by differentiating every coordinate, every function in the coordinate, function in every coordinate. Actually, we will touch this again, but this is required for here. So you can see that these three terms here are coming from R prime T. But how about these? So these are just the nebula F. Okay. So we have this. And then what does this mean? This means that the gradient vector dot with R prime T is 0. What does this mean? When dot product is 0, what does it mean? They are perpendicular. They are perpendicular. Okay. So here, this one is fixed. This R is an arbitrary path. Okay, that passes through P. Okay, so this means what? The gradient of this level surface is always perpendicular to the path that passes through the point S0, Y0, and Z0. No matter what path you draw, they are always perpendicular. Okay. Okay. Okay or not? Does it make sense? Okay. Does it make sense? So delta F here is a fixed one. It's already fixed by your level surface. Okay, this is fixed by your level surface. But R here is what? Is any path. Okay, any path that passing through S0, Y0, and Z0. Okay. So you have a fixed gradient and then perpendicular to any R prime. So what can we do about this? Okay, what can we do about this? What can we do about this? R prime T is what? Is the derivative of my path. Okay, so I think I need to draw some picture for you to imagine now. Let's draw some picture for you. Imagine. It's not image. Okay. So the easiest picture you should imagine is a sphere. Let's imagine a sphere. Let's imagine a sphere. Okay. Let's imagine a sphere. Okay. And then take a point here. Let's call it x naught, y naught. Okay. And then if you imagine a sphere here, you can try and take a path like this, for example, a path like this that passes through R. Maybe call it R1. Okay. We will do a lot of paths. So what's the R prime T at x naught, y naught, z naught? So what you do is you just draw a tangent line here. Okay, makes sense. Okay, and then you can also take another path, like R2, maybe R2 like this. Okay, and then you draw the tangent line also. Okay, you also draw the tangent line. Okay, let's draw the tangent line. Let's draw the tangent line. For example, like this. Right. Okay, so these are the tangent line. Of course, you can draw more. You can draw more, right? You can draw like this, for example. Okay, draw more tangent line. Okay. But what the calculation tells you? What does the calculation tells you? The calculation tells you that all these lines, for example, this is a R prime, R2 prime, okay, R1 prime, you know. So R1 prime, R2 prime, and then R3 prime. This vector is what? Is perpendicular to the delta F. It's perpendicular to the delta F. So where should the delta F be? Where should the delta F? The delta F should be some vector that coming out from the screen. Okay, some vector coming out from the screen. Okay, so it should be something like this. Let's say this is a delta F, big F. And then this delta BF is perpendicular to all these three lines here. Okay, does it make sense? Yeah. Sorry? Not necessarily. It's just a level surface. It's just a level surface, not necessarily a plane. It could be a plane. Yeah. Remember the example we did last time? So where is the level surface? So let's go back a bit. So let's back up. Let's back up. So let me find. Yeah. Okay. See, level surface here. X, Y, Z equals to some K. What is this? This is a sphere. Okay. So you get bunches of sphere. Okay. So it's not just plane. There are a lot more. As long as it's surface. At most you can get surface. Then you can get plane, you can get line, you can get dot. Okay. Yeah, so you could get a surface. Sorry. You could get a sphere. Okay, no? Yeah. Okay. So this means what? They are perpendicular to del F. So they live on the tangent plane. We can define tangent plane using this del F, and then this R prime will live, this line, tangent line will live on the tangent plane. Okay. So we can, because tangent plane actually is defined by, could be defined using the derivative of the path, all the path that passes through it. Okay. This is one of the definition. And then del F become the normal vector of the plane. So actually there are three definitions for tangent space. Tangent space. If you study differential geometry or differential manifold, you have seen two already. One of them is by the limit definition. The second is this one, using all the derivative of path. You can build the tangent plane. Okay, so let's go to the definition and then we'll take a break. So here, so in this case, so if nebula f is non-zero, then we will just define our tangent plane using the nebula f. Okay, so what is nebula f here? So we will rearrange the equation of plane. Okay, so what is plane? Plane is what? How to build a plane? What do you need for a plane? Again, a normal vector plus a point. Okay, a normal vector plus a point. So what is the normal vector now? It is del nebula f, because nebula f is the vector that is perpendicular to every derivative of path. Okay, derivative of all path. Okay, so you can see that A, B, C here are just the gradient vector of the level surface. Okay, no? Okay. So last time how we build the tangent plane? So remember last time how we build the tangent plane? Last time what did we say? We said that there are two directions is very important, which is x and y. So fx, fy. Okay, but it's slightly different last time. What is the setting for last time? How is our surface? So what do we have last time? Right. So last time we have given. Okay, make it smaller. So last time what is given? So we are given surface fxy. It's not fxyz equal to something. It's just fxy. Two variable function. Two variable function, you can define a surface. Right? Okay. So how to get the tangent plane? The plane of fxy. Okay, for example, similarly at s0, y0, z0. You must fix a point. Make sure you need to fix a point for tangent plane. Because why? Given you a surface, you must tell me which point first. Only I can find you a plane. Okay. You need to fix a point, and then I can tell you the plane. Okay. You imagine in y equals to x. Okay. For example, y equals to x squared. Okay. You need to tell me which point. Okay. Only I can draw you the gradient. Okay. You need to fix a point first. Right. Okay. So given a surface fxy, the tangent plane of fxy at x0, y0, z0 is what? Is the linearization. Remember the linearization? Okay, the linearization, which is z minus z0 equals to fx of x0, y0 times x minus x0 plus fy of x0, y0, y minus y0. Okay, so this is what we have last time. But here we got a big F. So what's the relation between big F and small f? Okay. This is very important. This is very interesting. We will talk about it next lecture. You can think about it first. So you see, I have two ways of getting tangent plane. Okay. But I start with a different description of my surface. So how are these two related? Which one is more general? Okay, you can think about it. Which one is more general? And then how these two is related? Does the first one imply the second one, or does the second one imply the first one? Okay, this is really dependent on how you describe the surface here. One is fxy, the other one is capital. So here is given, what is given here? Here is given the level surface. This is the difference between these two. Okay, so which one is more general? try and think about it. Okay, can you show that one of them imply the other? We will discuss this in the next opening lecture on Thursday. Okay. Yeah, we will go through this concept again. So I think the concept of this class, I need to go through at least 2 lectures so that you can fix inside your mind. So every notion I try to repeat in 2 different lectures so that keep revision for you. Is it okay? Yeah. So next, so on Thursday I will come back and discuss the relation between these 2 again. Okay. So for now, you need to see why we define tangent plane in this first place, and then recall that previously we have also a tangent plane definition, okay, and then see why these 2 surfaces give rise to different tangent plane. Do they imply each other? Can I get this tangent plane here using this capital F? Can I get the tangent plane of capital F using small f? Okay, so this is the thing I want you to think about. Okay. And then next lecture we will talk about this. Any question? No? No? Okay, let's take a break until 5:12. 5:12.那你没有看到？
另外有另外一个部分，
哪一个没有看到？从后面看起，你就从后面看起。
当那个里面有到三角形有变成零的时候就有问题了，然后就比那个完全
对，
但是我没有看到他有任何讲哦，讲到
那个是那个完整的 proof 还是什么
这完整的
？OK，完整 proof 哦，完整 proof 它没有经过那个 DK 等于零的东西啊，所以它不用担心，那件事情。
是他讲避免这种情况，
它避免的方法就是它把它展开哦。它把它展开，那个 DK 等于零其实是这个部分，如果没有记错，这个部分。但是它这个 K 啊，你看它放在上面了，and then K 为什么没有用？对，因为
你讲放在上面是这种
你没有开出来，你开出来吗？
对，
另外一个，你照给我看的那个 DK 有问题，下面是
是你讲的 DK 有问题哦，那个就是这边哦，那个
是这个哈，
这是下面这个，这在那边哦，还有然后这个钥匙的也是有，但是我看它的是深嘛，但是那个这个更难。
这个，OK，你看它 delta U，delta U 对，delta U 是这个部分，这个东西去零，是这个东西去零，OK，所以这个东西是 GX 加 delta X 减 GX 哦，OK，是这个部分去零，然后它这个 delta GX 这是这个部分，这个 GX H 加减掉 GX 是这个东西，它的 delta U 是这个东西，可以吗？所以他怎么避免掉刚才他做的事情呢？他就
你讲这边是整个区零，
对 delta U 去零嘛，it might be happen that delta U 等于零嘛，
是整个
对，这个东西就是零，不是去零，所以你要分辨
是零和去零的东西。去零我们是取零米，等于零就直接让它是零直接让它是零，所以它是直接让它是零。去零的话，我们会这样子写，这个叫去零，这个叫等于零。所以这个等于零，你看它等于零，所以这边为什么没有这种情况在呢？是因为你看，是因为它把它变成这里，它在去零有问题，是因为它拿来除它拿来除，它这一部分拿来除，所以这一部分如果是等于零，它这个 expression 就有问题了。但是它写的方法是拿来乘，所以 that's why 它这个 ek 跑出来。你知道什么是 ek 吗
？EK 就是
error，它的 error，它的那个误差between 这个两个东西。你知道这两个东西会有误差，你知道为什么吗？对，因为 by definition 这个东西是它的 limit，所以你如果还没有取 limit 的时候，它还不是它嘛，所以它会越来越靠近嘛，所以它会有误差。k 一开始大，它就开始有误差了。但是呢，它 define k 等于零的时候是零，为什么？因为 by definition 嘛，
对的，
by definition 它的 limit 一定要是等于它嘛，对不对
yes，
？limit 就是要等于它，所以意思说，还记得我那时候那个图嘛？所以那个两边靠近的时候，我丢掉一个点，所以你讲补这个点回去，define 那里点就是它咯。
所以这个是实际上是越来越接近那个 point 是零啊。
这这这，它越来越接近于它，所以这两个越来越近，像你相减一个越来越近的东西，是不是零？对，零哦。所以当他们 k 已经越来越小，他们越来越近的时候，他们就会去到零。
这个就是那个 f 的 derivative。
f 的 derivative 对 limit 你取 limit of 这个 secant 的话，就是这个对，然后
我知道这个 part 他在讲什么，
然后
但是我就是不是很明白他定义了这个 gx，然后
然后怎样？
讲到任何关于这个 increment
哪个 increment？
delta u 可能有点没有听懂。
delta u 刚才都说了哦，那个 delta u 是 gx 加 h 跟 g u 的部分嘛，所以它的这个部分在这里，它让 k 等于这个，这是你要看的东西，先是它的 k，
这是有
这是它的 k，这是你刚才的那个 u
的，
就是那个 delta u 是它的 k 这边，yeah，所以它意思是说什么？这个是 one variable，但是你要做 chain rule 嘛，所以你要 sub u 是等于另外一个方向，所以 u 变成 gx 哦。
yes，
所以 and then 这样 k 是什么呢？in 这个 case，这样 k 的话就是 g 的一些 difference 哦对不对？然后还有什么问题啊？它从 one variable 放 chain rule 进去，
等一下有一点 make sense 啊。
make sense，一定 make sense 的，不可能不 make sense。不 make sense 只是你有一些东西理解错吧？肯定要 make sense 的。
是它是一个，比如讲 gx，比如我们可以定一个空间 g，不管是 gx 会等于一个 constant，
对吗？然后
这个就是零了嘛。
sure，然后 OK，这样你加一个零有什么问题？
加一个零，你是讲这边
没有啦，u k 变成零嘛，因为 constant 减 constant，k 是零嘛，然后 u 是一个 constant 嘛， 所以是说 U 这边是一个数字咯 ，F on 一个数字不是只是 evaluation 吗？
Yes，
对不对？然后 F evaluation on 这个 evaluation，所以你是说会出现零除零啊？嗯给我看一下啊。想一下。零，就这个 constant 的话，因为如果是一个 constant 的话哈，你就只是 check F 在某一个点上面吧，不是？你是说如果 G 是 constant 的话，会发生什么事情呢？
嗯，
OK，等一下我再帮你想一下。
对，
那边等等。
我看看，OK， let's continue this. Okay, try and find this. So let's try and find this. So let's get the formula out. Okay. So just now I told you about the equation of tangent plane for level curve, but how about the normal? Okay. You know what's the normal curve is? Sorry, not the curve, normal line. What is this line about? Hmm. Let me see. What's the normal line is? What's the normal line? What's the definition of a normal line? Yeah, I think you're right. Okay, so what's the definition of a normal line at the point of a surface? Normal. Normal is mean what? Oh, okay, good. Okay, what's a normal line? What's the definition of normal line? Perpendicular. Perpendicular to the tangent line. Okay, good. So, let's put the definition here. Okay. Is a line that is okay, so let's define a normal line at a point on the surface. Okay, so what is this? So this is a line that is perpendicular to the tangent plane of at okay at that point. And let's give the point a name. Let's call it P. So at the point P. Okay. So what is this? This is just the normal vector for your tangent plane. Okay. Yeah. Okay. So let's do it. Yeah, do it. So how to do? So just now we say that the equation of a tangent plane, equation of tangent plane for a level surface is what? Okay, so what's the equation just now? The capital F at S, okay, evaluated S naught, Y naught, Z naught times X minus S naught plus Fy X naught, Y naught, Z naught, Y minus Y naught plus Fz times S naught, Y naught, Z naught times Z minus Z naught equal to 0. Okay, so how to compute this? So try and compute this and then we compare answer. Yeah, try and compute this and then compare answer. We will compare answer. So what's the capital F here? So the capital F here is just x squared over 4 plus y squared plus z squared over 9. Okay. So does it matter what k here or not? Let me ask you. Does it matter what k here? If I change to 5, does it matter? 6? Okay, it doesn't change my partial derivative actually. Okay. Yeah, so try and compute what is fz, fy, and okay. Anyone got the gradient vector yet? Anyone got the gradient vector? What's the gradient vector here? Minus 1, 2, and what? Minus 2 over 3. Did everyone got this? Did everyone got this? Fx, Fy, and Fz at the point S naught, Y naught, Z naught. Everyone got this? Got this? Okay, so to get the plane, what do? You just sub this value in. Okay, so minus 1 times x minus 2 plus 2 times y minus 1 plus minus 2 over 3 times z minus 1. Okay, this thing equals 0. So what is this? This is 3x minus 6y plus 2z plus 18, 0. So this is the description of the plane on my surface here. Okay, so this is the description of this plane. But how to get the line? How to get a line? You know the normal vector, meaning you know the direction. Okay, you know the direction. And then you know the point. Okay, so I can build a line. So how to build a line? Can recall now how to build a line. How to get a line. Actually, this is a similar concept you learn in finding a null space, what space, null space before. Yeah, in your linear algebra. The null space you find is a space, right? What kind of space? Sometimes it's a line, sometimes it's a surface. Okay, so let me pull out the page first. Yeah. Have you guys proved something is a null space or colon space or what? Anyone can recall now what you do in linear algebra? What's the variable you call in the null space? What's the variable you call? I don't recall now. What's the variable you call? Remember, you write something like, yeah, maybe some like this, and then plus t times something. Does this seem familiar or not in linear algebra? Like this. What do you call this again? What variable is it? Free variable, yes, free variable, correct. Free variable, correct. Yes, free variable, correct. So what are you actually doing here for this solution? Let's say the null space is this. What is this? Set of point, set of solution, correct? Set of solution. So you need to think of it geometrically. These are the point in R3, right? So this is the point in R3. This is also a point in R3. But the point also represents a vector. So which one is direction? Actually, this is the direction because you can scale the free variable here. So what is this? This is actually a line. That's why you call it a null space or whatever space. It is a space. Okay, it's a line. Okay. So how you describe a line? So how to describe a line? So a line L. A line L is described by a point on L. Okay, a point on L. So let's call this line L. A point on L and the direction of L. Okay, so same case, for a line, you need a point and a vector. Okay, the vector that the line points to. For a plane, you also need a point and a vector, but the vector is normal to the plane. Okay, this is the difference. Both of them, you just need a point and a line. You can build it. So how do you build this line here? So the line is equals to some point. Okay, let's give the name for this point, right? So let's name it as A naught or S naught, perhaps. S naught, Y naught, and Z naught. Okay, so you need a point, okay, plus a direction. So what's the direction? Maybe call it S, Y, Z. Okay, S, Y, Z. S, Y, Z. So what do I do to S, Y, Z? I scale it 50. Okay, so this is my line. Okay, not that there's a slight difference. I treat this vector here. So the first here, the first there, I put the square, the round bracket because I want to see it as a point. Okay, but the bottom here, I put like the what do you call this? This I think in latex we put L bracket. I'm not wrong. Okay, so I put this. Let's call it a square bracket. Okay, so I can put like this. So I can even put like this. So let's put it as a square bracket or a row vector. Okay, row vector or column vector here, because this direction here we regard it as a vector, direction vector. Okay. One, I want to see it as a point. First thing I see it as a point. Second thing I see it as a vector. Here I treat both of them as a vector. So we can go back and forward. So let me write down this fact here. So a point in Rn is equivalent to a vector OP. Okay, let's call this point P in is equivalent to a vector starting from the origin. Okay, all these vectors are starting from the origin. Okay, okay, no? Okay, so how to get the normal line? So how to get the normal line? So equation of normal line is just, let's say we call it nt equals to, where's the point we started? So we start at minus 2, 1, minus 3. Okay. So minus 2. So minus 2, 2, 1, and minus 3 plus t times syz. So our syz is minus 1, 2, and minus 2 over 3. Okay, let me move everything down then. So let's apply this. Let's see how we find the, so we want to find of normal line. Okay, let's find equation of normal line. So our normal line have this which is minus 2, 1, minus 3 plus t times minus 1, 2, minus 2 over 3. Okay. But this is just a function, right? Function in t. Okay, this is a function in t. Okay, this is the function in t. It's not quite an equation yet. So what's the equation they need? So you can rewrite this, right? You can rewrite this as s equals to minus 2 plus, so minus t, y equals to 1 plus 2t, z equals to minus 3 plus, so minus 2 over 3t. Okay, you can write it as, what is this called again? You still remember in your linear algebra? Parametric solution, right? Okay, so this is the parametric solution. So how to get equation out of here? How to get equation? How to get equation? What are the same here? Out of these three equations, how to get a single equation? Huh? Okay. That one. So what do? You kill all the t variable. Okay, how to kill all the t variable? Yeah, move t to one side, right? Move t to one side. So individually, what do you have? T equals to minus x plus 2, right? Yeah, in other words, okay, in other words, I will write x plus 2 over minus 1, and then t equals to y minus 1 over 2, and then t equals to, in this case, what you get? This is a bit long, so t equals to z plus 3 over 2 over 3. Okay, so you have three equations for t. Okay, so you can equate them. Okay, you can equate them. So altogether, you get x plus 2 over minus 1 equals to y minus 1 over 2 equals to z plus 3 over 3. And then this is called the, this is what's called symmetric equation for a line. Okay, So why is this useful? How is this a symmetry equation for a line? You can see that all the denominator here is actually the normal line. It's a normal vector. Okay. And then all the factor here, right, is the point where you look at the normal line. Okay. So this is another way to write a line. Okay. So just now we can write line using this point time, a scalar of your direction vector, or you can write it in terms of the symmetry equation. Okay. Any question? So these are different way of writing a line. So the most important line I think is this one. This is what you need to know. A point at a scalar multiple of your direction. Okay, from there, and then you can work out these equations. Okay. Any question? No. Yeah. Okay. Okay. So most important is this line. This line very important. Point plus a scalar multiple of your direction. Like that. This one very important. So direction you can scale it. Okay. Or maybe let's keep going on. Okay, we will introduce a new notion now. Maximum and minimum value. So what's the maximum and minimum value? So we have two types of maximum and minimum value. Okay. So we have local and absolute. Okay, so what does it mean by local and absolute? Local means if I just look absolute around me, okay, I'm the tallest. But so maybe Chun Jack is the tallest guy in this class. Okay, this is local maximum. But when I compare to the whole world, maybe is it called Yao Ming? Yao Ming is 200 meters, so it's taller than Chun Jack. And if you found out of every world, every place in the world, Yao Ming is the tallest, then Yao Ming is the absolute maximum. Okay. So absolute maximum meaning if you compare to the everything, you are the maximum, then you are absolute maximum. Similarly to absolute minimum and local minimum. Okay. So if you are just locally, you can find a neighborhood, you are the minimum, then you are locally minimum. But if you compare with all the minimum, you are not the least, then you are not the absolute minimum. Okay. So absolute minimum meaning you are smaller than every point in this world. But local just need the neighborhood point. Okay? As long as there's a neighborhood for you to be minimum or maximum, then you are locally maximum or minimum. Okay or not? Okay. So let's go through this definition in detail. So what is absolute extreme values? So let's say you have a function with domain D, okay? And then let P naught be a point D. Then Fp naught is absolute maximum if Fp naught is greater or equal to every point, okay, every Fp in your D. Similarly, for absolute minimum value, it is smallest and equals to every Fp in your D, okay, for P in your D. So we will say that a point is absolute extreme value if either one of them is true. It cannot be both true, right? You cannot be both maximum or minimum. Or you can when you are a constant. You can, okay, when you are constant. When you are a constant function. Okay? Yeah? Okay, so how about this? So when it is local minimum or maximum means what? So if it is local maximum, if Fp naught is local maximum, means there exists a neighborhood n of P naught such that Fp naught is greater or equal to P, okay, around that point. Okay? If it is local minimum, then it is Fp naught less than or equal to Fp, okay, for all P in the neighborhood. And it is a local extreme value, either one of them is true. Okay. Okay, no? So here, right, I think since you are mathematics students, you should know what is neighborhood. What's neighborhood? I haven't defined neighborhood yet. What's neighborhood? What do you think? What is neighborhood? What's neighborhood? 邻居啊，社区哦，okay, better. Okay, so what's the neighborhood? Okay, so let's define what's neighborhood. Okay, it's very close related to what you think it is. So how is a search work? All right, so you cannot just say neighborhood, right? Who is nearby? Okay, so you need to tell me who are the nearby people. Do some definition. So who are the guys that are nearby around you? Okay, so we fix a picture around me. So who are nearby? So if you see the radar in maybe aeroplane or plane, right? So the neighborhood is something like a circle. Okay, so we'll define what is an open disk first. Okay, let's define what is an open disk. Then so we'll denote. There's two things to denote here. Like circle, right? Circle, what's the two things I need to know? The center and the radius. Okay, similar to this open disk here. So an open disk in R2, okay, with radius delta greater than 0 and center AB is the point. Okay, all the point. Okay, all the point. So what are the points I'm picking? These are the points that such that the distance between them and my center is strictly less than delta. Okay, strictly less than. So meaning I don't pick the boundary. I don't pick the point exactly on the circle. I just pick everything inside the circle. Yeah, I just take everything inside the circle. Okay, I don't take the boundary. So that's why I said open. Okay, it's open. Okay. In this case, what? In this case, we will say that neighborhood n of P in R2 is an open is containing. Okay, so what is a neighborhood? 方圆百里的人就是我的 neighborhood。对吗？方圆delta 就是我的 neighborhood。Let's say I'm here. Okay 吗 ？Okay. Okay. Yeah. So a neighborhood of a point P meaning is an open disk contain P. Okay, as long as it's an open disk, that's all. That's all. Fine. Okay, so I need to go into one deeper concept before we introduce the next theorem. So let's do definition here. Actually, this concept live in topology, so you'll see it later. The later course. So a set S in R2 is called open. Okay, just now I defined open disk for you. Now I want to tell you what kind of set is called open. Okay, what kind of set is open? So if for every element in my set, what do you think? How is a set open? What do you think? When is a set open? What can I do to the element in my set? I have opened this now, so what can I do? Try and guess. I can find limit of the border, not quite. I can cover my point. Okay, I can cover my point with a disk. Okay, around it, such that this is lying inside my S. Then my set will be called open. Why am I doing here? What am I doing here actually? So for example, just now here, yeah, let's pick this example again. Let us ask a question. Is an open disk open? Of course, we want it to be open, right? So let's check. Open disk is open. Otherwise, this is useless, right? You define something is open, but when I say open, this is not open. Right or not? So we must make sure my open disk is open. Okay. Okay. So when I want to prove open disk is open, what does it mean? Every point inside my open disk, I can find a ball or an open disk, which is lying inside the set open disk. Okay. So meaning what? Meaning if I take a point inside my open disk, correct or not? Okay, I need to be able to find a open disk which is lying inside the open disk I started with. Can I do that? Can I do it? Or can I do it? Can I do it? Do you get what you need to do? So for every point inside this open disk, okay, I need to find a open disk that covers this point, which is lying inside the X. So here is my S now. So my S is this open disk. Okay, can I always do that? Can I always do that? How? How? Correct. You can choose a set of it because this definition saying that exists. You just need to find one. That's enough. You can pick your favorite. This. Okay. So how to pick? Let's say I fix you a. Let's say this is 1, 2. Okay. So this is at 1, 2. Let's say this radius is like maybe 3, right? So how do you check it? So if I pick any point within this here, can I always find? Okay, can I always find a ball that cover this point, which is always lying inside S? Can I always do that? Can I? Let's say for this, let's call it, what's this? Maybe 1, 3. Yeah. Can I find the circle like this or not? Can I find circle like this? Can I find circle like this? No, right? Because it will contain something outside this. Okay, so you need to make it small enough. Okay. Can you always do that? Can you always do that? Can, right? How? Yeah. Make the radius smaller. Okay, so you just make this radius smaller. Okay, make it smaller until it is entirely inside the disk. Okay, so how small you should take? All right, so this is the question always asked in analysis. How small you should take? Okay, so there's a precise way to get the small number here. Yeah. So what distance you need to compare? So the largest you can go is only this 3 here. Okay, so you need to check what's the distance between this point and this 3, and then this point with center, and then you pick the middle. value. Okay, minimum of these two, the middle value. Then you can pick a small circle here. Okay or not? Does it make sense? Yeah, try work it out. Write yourself. Otherwise you will forget. You just listen to that and then tomorrow you forget already. Because this idea is new for you, so you have to repeat it. Okay, everything new you have to repeat it. If you don't use it, and you will be forgetful. Okay, so why I introduce this open set here? Because I want to introduce what is closed set. Okay, so I'll define a set C in R2 is closed. Okay, it's called closed if this closed set is a complement of an open set, of some open set. Okay. Okay, because we want close. Okay, so a closed set, if you can write it as a complement of some open set. For example, what is close? This is close. Okay, what's close? This. So just now we don't include the boundary, right? So when we talk about close this, we will include the point, all the point, including the boundary point. So we will include all the boundary point. So in picture, how should you picture it? So we just take all the point, including all the boundary point. Close this. Okay. So in this case here, when I say this is close, right, meaning this is R2 slash by some, take away some S, okay, for some open X. So what is open here? So it's just, so I just take, so this open S should be what? R2, take away this close 4. Okay. Yeah. So if you imagine, so R2 is infinite, right? So R2 is infinite. So let's imagine this is R2. Okay, R2 is actually infinite. Yeah, infinite. And here middle is the C. Okay. C. So if I take away the C, what happened? What do I get? I just get picture like this. Okay. And then this thing is open. This thing is open. Okay, why is it open? If you pick any point here, you can make your ball to avoid this boundary here. Right? But this one is infinite this way. All the way is infinite, so it's okay. But the problem is don't touch this boundary here. Okay, so how to not touch the boundary? So you need to make sure you are at least the radius away from the center of your ball. You can try and work it out, okay, using a specific example, like just now. But at least you need to get the idea. Okay, you need to get the idea. Okay, no. Probably we will have a question on next assignment about this thing. Yeah, open and close stuff. Yeah. Okay, so why we talk about this? Because this extreme value theorem here. So if f is continuous on a closed bounded set D, then f will have absolute maximum and absolute minimum there. Okay, so this is the theorem. This is the there's the calculus 1 theorem, right? What is it called? Also the same name, is it? Extreme value theorem. So if you have a closed and bounded interval, and then you have continuous function there, you must attain your absolute extreme value on this interval. Okay, this is the same for higher dimensional case. But what are the closed and bounded
set here. So for example, here are closed and bounded. Okay, you can see that when it is closed and bounded, the boundary are included. But if it's not closed, then the boundary might not be included. Maybe you include part of it, but not all of it. Okay. Yeah. So how you should imagine this? This is just domain. This is just domain. So meaning what? Meaning you are the surface like this, maybe. Okay, you have a surface at the top here. But here is the part that corresponds to the domain below. Okay. So these pictures are just picture in the domain. Okay. So you need to imagine a surface on the top. And then you project the domain up using fxy. Right, fxy give you the height of the xy. So it is a point that living on the surface. Okay. Okay. We will repeat this theorem again, and then we repeat the tangent plane again on Thursday. All right. Okay. Any question before we break? Oh, okay. Yeah. If not, we will continue next on Thursday. Okay. So see you on Thursday. Please, you can send me in your draft for this week, and then due on Tuesday. Yeah. Yeah. I'll put out the link and the procedure that you need to do soon. Just send me